I'm a distinguished research fellow here at the Gemological Institute of America in Carlsbad, and I'd like to give you a brief overview of the situation today regarding synthetic diamonds. Gem quality synthetic diamonds are becoming more available in the jewelry marketplace today, and this has created interest and some concern among jewelers regarding what this material is and how it can be identified. I think the good news is that synthetic diamonds have been extensively studied over the past 30 years, and today we know a great deal about how they are grown artificially and how they can be recognized. What I'd like to do is to give you an overview of synthetic diamonds, how they're grown, and how they can be recognized, and in terms of gemological properties that a jeweler can look for or a person in a gemological laboratory. I think the first question is, what are synthetic diamonds? Although they're produced artificially in a factory or a laboratory, synthetic diamonds correspond very closely in terms of their chemical and physical properties to those that are exhibited by natural diamonds. Synthetic diamonds are sometimes referred to in the jewelry trade press as a diamond imitation or a simulant, but this is incorrect. A diamond imitation or simulant, I think the best known ones today are cubic zirconia and synthetic moissanite, but synthetic diamonds fall in a different category. Although cubic zirconia or synthetic moissanite are similar in appearance to natural diamonds, these imitations have very different chemical and physical properties compared to those of natural diamonds, which allow them to be readily identified by a trained gemologist using, for example, a thermal tester to detect cubic zirconia. However, synthetic diamonds cannot be detected by these simple methods, or at least the use of these simple testing instruments. A wide variety of natural, synthetic, and color-treated gem diamonds are available in the marketplace today. And because they differ greatly in commercial value, proper identification is important for both valuation and proper disclosure to consumers at the time of sale. In some cases, these synthetic and treated diamonds can be recognized by a trained gemologist using standard gem testing equipment. In other instances, however, positive identification must involve testing the diamond using advanced scientific instrumentation in the GI laboratory. In the GI laboratory, we've developed a large database of information on the gemological properties of diamonds of all kinds, and we use this database to help develop additional means of diamond identification. Before talking about synthetic diamonds, let me say just a couple of words about natural diamonds. Natural diamond crystals formed millions of years ago deep in the earth at depths of perhaps 100 miles or more, and at a much later time were brought to the surface by an explosive volcanic eruption, which formed a narrow vertical pipe of igneous rock called kimberlite, and on the right-hand side a natural diamond crystal. Mining of these kimberlite pipes is carried out to recover the diamonds. The ore is mechanically broken down to liberate the crystals. Because the amount of diamond in kimberlite is very low, perhaps 1 part diamond per million parts rock, a large amount of kimberlite ore must be processed to recover the diamonds. The ideal shape of a diamond is an octahedron, which is an 8-sided geometric shape with triangular-shaped crystal faces. A diamond growth is taking place on all of the 8 crystal faces, so the diamond is growing outward from the center toward the outer edge, and that kind of gives a kind of a concentric square pattern of a growth pattern if you look at the diamond with special equipment under the microscope. The basis of identifying diamonds here at the GI laboratory and other organizations is what is referred to as the diamond type. We're going to say just a few words about this diamond type classification system. Beginning in the 1930s, scientists began to recognize that certain kinds of diamonds displayed similar properties. For example, blue diamonds often exhibited electrical conductivity. And they grouped these diamonds at the time into 2 main categories, which were referred to as type 1 diamonds, shown here at the top, and less common type 2 diamonds, shown at the bottom, based on differences in their transparency to ultraviolet radiation. Somewhat later, in 1959, it was found that nitrogen was the principal chemical impurity in natural diamonds, and furthermore that type 1 diamonds contained nitrogen, where type 2 diamonds did not. Both type 1 diamonds on the top row and type 2 diamonds on the bottom row can be further divided into 2 subcategories, as shown in these illustrations, which depict a simple representation of the arrangement of carbon and impurity atoms in the diamond structure. Starting with type 1b diamonds at the top right, you see the nitrogen atoms indicated by the N symbols as single nitrogen atoms in the structure replacing carbon atoms. Type 1A diamonds at the upper left also contain nitrogen, but in this case the nitrogen atoms are aggregated, that is close together. And again, type 1A and 1B diamonds are the natural nitrogen-containing diamonds. Type 2 diamonds don't contain nitrogen. If the diamond contains a small amount of boron, indicated by the letter B in the lower right-hand diagram, it's what's referred to as a type 2B diamond. And if the diamond is quite pure chemically, there's almost no impurities, it's a type 2A diamond. This is just a simple way of dividing diamonds or categorizing diamonds based on the physical properties. And this diamond type can be quickly determined by a scientific method called infrared spectroscopy. Well, you might ask, why is this diamond type classification important for recognizing synthetic diamonds? I put together this chart shown on the slide where there are 4 type subcategories on the left-hand column, and then natural, and then the 2 types of synthetic diamond growth processes also shown. The vast majority of diamonds in nature are type 1A diamonds with aggregated nitrogen, but it's not possible to produce these aggregated nitrogen diamonds by synthesis. So you see those boxes are blank on the graph, on the chart. What's produced in the laboratory are type 1B, type 2A, and type 2B diamonds. These are all quite rare categories of diamonds in nature. So I think one of the first steps we try to make is determining, is it a type 1A diamond, which means it's a natural diamond. And if it's found to be one of the other 3 categories, it could be either natural or synthetic, and that needs to be determined by additional testing. Now let's talk for a few minutes about synthetic diamonds. Synthetic diamonds, that is artificially produced diamonds that are grown in the laboratory, were first produced in the mid-1950s as very tiny single crystals. Production of larger crystals that were suitable for faceting for jewelry use began in the mid-1990s and continues to the present time, with more companies being involved with synthetic diamond production. We just show here in the photo some examples of gem-quality synthetic diamonds, some of them mounted in pieces of jewelry. Today, synthetic diamonds are grown by various companies in several countries for both jewelry and industrial applications. And in fact, the industrial applications of diamond may be much more important than their use in jewelry. Of course, in nature, diamonds grow over a very long period of time and have a residence in the earth of millions of years. In contrast, synthetic diamonds grow in a very different way in the laboratory. Synthetic diamonds grow over a very short time, several weeks to perhaps 1 month or more, under conditions that are different from natural diamond formation deep in the earth. There are 2 methods for producing a synthetic diamond in the laboratory. One involves high pressure and high temperatures. It's oftentimes referred to as HPHT growth, where you're producing the diamond from a molten metal flux using a seed crystal. This is the traditional method that was first developed beginning in the mid-1950s. The newer method, which involves growth at low pressures and high temperatures, which is oftentimes referred to as CVD or chemical vapor deposition growth. This is growth of a diamond in a vacuum chamber from a gas, such as methane, using diamond seed plates. These are the 2 methods, and because they are so different than the conditions of natural diamond formation, this results in the features that can be used for their identification. On this slide, I show kind of a graphical depiction on the left-hand side of this high-pressure, high-temperature growth apparatus where the diamond is growing in a very small little capsule. HPHT diamond growth takes place in a small capsule positioned in an apparatus capable of generating very high pressures. Within the capsule, diamond powder starting material dissolves in a molten metal flux and then crystallizes out on a seed diamond to form the synthetic diamond crystal. Crystallization occurs over a period of several weeks to a month or more to create 1 or more crystals. Because of the very short growth period, synthetic diamonds grown by this HPHT method display a shape that is very different from natural diamond morphology. I show here in the center, and there's a photograph of 2 crystals on the right-hand side. In this case, you have diamond growth in 2 directions, indicated by the 2 arrows. So it's growing outward on the yellow crystal faces, which are the octahedral faces, the same as on a natural diamond. But it's growing also on the blue crystal faces, which are the cube crystal faces. This type of growth is not seen in natural diamonds. And finally, the crystal has a flat base. So as you see on on the photograph on the right-hand side. These HPHT grown synthetic diamonds have a very different crystal shape than the natural diamond octahedra I showed a moment ago. These HPHT grown crystals are typically yellow and now increasingly colorless. Blue and other colors are less common. But this is the typical shape where you have growth in both the octahedral and cube directions to produce this crystal, kind of what's referred to as a cubooctahedron with a flat base. The more recently developed method for producing a synthetic diamond involves growth in a vacuum chamber filled with a carbon-containing gas, such as methane. A source of energy, like a microwave beam, is shown through this gas, which causes the gas molecules to break down, and the carbon atoms are attracted downward to a flat diamond seed plate. So in the illustration on the left-hand side, you see the gas, which is kind of shown in red. It's a high-temperature plasma. You have the microwave energy beam, which breaks down the gas molecules, and the carbon atoms then are attracted down to this array of seed plates at the base of the chamber. Crystallization again occurs over a period of several weeks to create a number of crystals at the same time, depending on the size of the chamber and the number of seed plates that are used. In the center, I show this diagram where the crystal is really growing in one direction. It's growing in the cube direction to produce kind of a tabular-shaped crystal. As shown on the right-hand side, the two photographs, these crystals have oftentimes a rough edge of black or grayish graphite. They oftentimes display a brown color, which can be removed by heat treatment prior to the crystal being faceted for jewelry purposes. Again, because of the very short growth period, CVD-grown synthetic diamond crystals display a shape that is very different from that of natural diamonds. And because the shape is a reflection of the internal structure of the synthetic diamond, again, this is the type of features that form the basis for their identification. Well, over the past few years, we've seen a lot of developments in the synthetic diamond industry. There is increased production for jewelry use. There is more companies involved. There are both what are referred to as grown colors, that is the colors as a result of the growth process, and also treated colors that are due to post-growth treatments. There have also been continued efforts and continued improvements in the clarity, the color, as well as the carat weight of synthetic diamonds. However, considering the number of reports about synthetic diamonds that we see in the jewelry trade press, we actually only encounter a very small number of synthetic diamonds that are submitted apparently unknowingly for grading reports to the GIA laboratory. While a trained gemologist may be able to recognize them, synthetic diamonds can be identified by the GIA laboratory. I show here in this next photograph the typical standard gem testing equipment that a trained gemologist would use for gem identification. It includes, from the front, a refractometer, a fluorescence lamp, a binocular microscope, a laryngoscope, and additional testing tools. A gemologist can identify a wide range of gem materials using this equipment, and there are some features that a gemologist can look for synthetic diamond identification.